Download this code from codegive.com, link in the description below. OK, let's dive into advanced spatial analysis within Leaflet using turf.js and potentially integrating it with tektronix, although the direct integration with tektronix depends heavily on what kind of tektronix data you're dealing with, so we'll focus on general strategies for bringing external data in. Introduction: the power of spatial analysis on the web. Spatial analysis used to be confined to desktop GIS software like arcgis or qgis. But with libraries like turf.js and mapping tools like Leaflet, we can perform powerful geographic calculations and visualizations directly within web browsers. This opens up new possibilities for interactive mapping applications, data-driven storytelling, and real-time analysis. Leaflet *, a lightweight, open-source JavaScript library for mobile-friendly interactive maps. It handles the core mapping functionality, displaying tiles, handling user interactions, zoom, pan, clicks, and rendering markers, polygons, and other geometries. *turf.js *, a modular geospatial engine written in JavaScript. It provides a vast array of functions for geoprocessing, buffering, clipping, simplification, intersection, union, difference. Spatial queries, finding points within polygons, nearest neighbors, calculating distances. Geometries, working with points, lines, polygons, multipoint, multiline string, multi-polygon. Spatial statistics, calculating density, conducting hotspot analysis, though not as extensively as dedicated statistical packages. Routing and navigation, limited simple route calculation, but usually requires external services for complex routing. Tessellation, converts polygons to triangles for 3D rendering or simpler calculations. Tektronix, integration strategies. Tektronix is primarily known for test and measurement equipment. Integrating its data into a web map requires a few steps. 1. Data export. Export data from Tektronix equipment, example oscilloscopes, spectrum analyzers, into a standard geospatial format, GeoJSON, CSV with coordinates, etc., or a format that can be easily transformed into one. The specific format depends on the type of data being collected, location of measurements, sensor readings, etc. 2. Data transformation. If the exported data isn't already in a usable geospatial format, use a server-side script, Node.js, Python, etc., to transform it into GeoJSON. Libraries like GDAL, Geospatial Data Abstraction Library, can be very useful. 3. Data loading. Load the GeoJSON data into your Leaflet map using techniques discussed below. 2. Setting up your environment. 1. HTML structure *. 2. Leaflet initialization *. This creates a Leaflet map centered on Los Angeles with a standard OpenStreetMap tile layer. 3. Core spatial analysis techniques with turf.js. Let's explore several fundamental spatial analysis operations using turf.js. 1. Creating geometries *. Important notes. Coordinate order turf.js uses longitude, latitude order. Leaflet usually expects latitude, longitude. Be very careful to swap coordinates when converting between turf.js geometries and Leaflet layers. GeoJSON turf.js works seamlessly with GeoJSON, which is a standard format for representing geographic data. 2. Buffering Buffering creates a polygon that represents the area within a specified distance of the input geometry. 3. Spatial queries, points within polygons *. This example creates random points and then finds which of those points fall inside the polygon you created earlier. Turf.points within polygon requires a feature collection, hence the use of turf.feature collection. Points within .features includes, point, does not work as intended, and will result in false positives. To solve this issue, use the following code for the if statement to check if the point is within polygon. If, turf.boolean point in polygon, point, polygon. For distance calculation asterisk. Calculates the distance between 2 points. You can specify different units, kilometers, miles, etc. 5 intersection asterisk. Calculates the area where 2 polygons overlap. 6 union asterisk. Combines 2 polygons into a single polygon representing the total area covered by both. 4. Advanced techniques and considerations. 1. Asynchronous operations, important for large data sets. Turf.js operations are synchronous, which means they can block the browser's main thread if you're working with very large data sets. To avoid this, use web workers to offload the calculations to a background thread. Asterisk explanation asterisk. The main script creates a worker object. It sends a message to the worker with the data and the type of operation to perform. The worker performs the turf.js calculation and sends the result back to the main thread. The main thread then processes the result and updates the map. Asterisk note asterisk. You'll need to serve these files from a web server, example using Python mhttp.server, for web workers to function correctly. 2. Vector tiles asterisk. For extremely large data sets, consider using vector tiles. Vector tiles are pre-rendered chunks of geographic data that are streamed to the client as the user zooms and pans the map. This significantly improves performance compared to loading the entire dataset at once. Libraries like Mapbox.js can be used to style and render vector tiles. Turf.js can assist in pre-processing the data to generate the vector tiles. 3. Heat maps asterisk. If you have a large number of points, example sensor locations, event locations, consider using Leaflet's heat map plugin to visualize the density of points. Turf.js can be used to perform kernel density estimation or other spatial statistics before creating the heat map. 4. Spatial statistics asterisk. While turf.js provides some basic spatial statistics functions, for more advanced analysis, consider using libraries like JStat or integrating with a server-side statistical environment like R, using an API. Examples include calculating point density, performing spatial autocorrelation analysis, or creating choropleth maps. 5. Real-time data updates asterisk. If you're dealing with real-time data from Tektronix equipment or other sources, use WebSockets or server-sent events, SSE, to push updates to the client. When new data arrives, use turf.js to perform any necessary spatial analysis and then update the map accordingly. V. Integrating Tektronix data, specific examples and strategies. The best way to integrate Tektronix data depends entirely on the data format and the type of analysis you want to perform. Here are some common scenarios. 1 scenario, GPS coordinates from Tektronix equipment, example site survey. Asterisk data format asterisk CSV or text file with columns for latitude, longitude, and possibly other measurements, signal strength, etc. Asterisk steps asterisk. 1 server-side transformation, node.js example. 2 client-side loading asterisk. 2 scenario, spectrum analyzer data, frequency versus amplitude at a location. Asterisk data format asterisk. This is more complex. You might have a file that contains a location, latitude/longitude, and then a series of frequency/amplitude pairs. Asterisk steps asterisk. 1. Server-side processing asterisk. The server-side script needs to asterisk parse the tektronix data format, which is likely proprietary. Asterisk create a GeoJSON feature. The feature might be a point with properties that contain the frequency/amplitude data. 2. Client-side visualization asterisk. You would load the GeoJSON as above. The point toLayer function would be more complex. Instead of just showing a marker, you might asterisk create a pop-up that displays a chart of the frequency/amplitude data, using a charting library like chart.js. Asterisk use the amplitude data to control the color or size of the marker, example higher amplitude equals larger, redder marker. 3. Example asterisk. Asterisk important considerations for tektronix data asterisk. Asterisk data format documentation asterisk. You must have detailed documentation of the tektronix data format. This is essential for writing the server-side parsing script. Asterisk units of measurement asterisk. Be very careful about units of measurement, degrees, meters, kilometers, dBm, hertz, etc. Make sure your calculations are consistent. Asterisk data validation asterisk. Validate the tektronix data before using it in your spatial analysis. Check for missing values, incorrect data types, and outliers. Asterisk coordinate systems asterisk. Ensure that the tektronix data is in a standard coordinate system, example WGS 84, which Leaflet uses. If not, you'll need to perform a coordinate transformation. 6. Best practices. Asterisk modular code asterisk. Break your code into smaller, reusable functions. This makes it easier to test and maintain. Asterisk error handling asterisk. Implement robust error handling to catch potential problems, example invalid GeoJSON, network errors. Asterisk performance testing asterisk. Test the performance of your application with realistic data volumes. Identify bottlenecks and optimize your code accordingly. Asterisk documentation asterisk. Document your code thoroughly. This will make it easier for you and others to understand and maintain your application. Asterisk user interface, UI. Design a clear and intuitive UI for users to interact with the map and spatial analysis tools. This comprehensive tutorial should provide you with a solid foundation for performing advanced spatial analysis in Leaflet using turf.js and integrating data from external sources like tektronix equipment. Remember that the specific implementation details will depend on your specific data and requirements, but the general principles outlined here should guide you in the right direction. Good luck.